So next is Mike Gamble. So I'd like to welcome everyone. I'd like everyone to welcome back to our event, Mike Gamble. Mike has been here before. He is a semi-retired Boeing engineer who managed an R&D lab, experimented with advanced engineering concepts, and he'll be presenting a comprehensive study on the Earth's gravitational system, not just its surface acceleration. His focus is not on the big G, the universal gravitational constant, but instead on the little g of Earth. He will be showcasing research based on Tesla's work, as well as providing tutorials on waves in general and mathematical modeling. He'll also discuss the wow moment in his research when math simulations lined up with observed results. So Mike, let me, if you'd like to unmute yourself, sir, and I'm looking for you in the list right now. Ah, there we go.
Okay, I think I'm off.
Perfect. Mike, there you are.
Okay, I need to load up my okay, let's see here. Uh-oh, I lost you guys.
Okay, so yeah, if you do the share screen button, that's
what I was looking for, but hang on. We hit this one first.
And no stress.
I think we'll get it this time. Okay, we're correct now?
Perfect, perfect. Okay, I will mute myself and feel free to go at any time, sir.
Okay, hang on. There we go. Okay, to start with, this presentation has been out in public domain for about 10 years. It was originally pitched at the Space Propulsion and Energy Science back in 2009. And since then, it's been all over the web and went all around the world in less than 2 weeks. I'm still looking for somebody to shoot it down. Nobody has proved it wrong in 10 years, but I'm still looking. If you Google my name, study of gravity, you will find both of these pitches. This is a two-part presentation. So we'll get started. It's a little bit long. Okay, the first one is the pitch release. I work for Boeing, so everything that was released has to go through the release system. And this is the memo that allows it to be in public domain, and the reference number, as long as those are intact, you don't have any problems with it. Next one here. This was when I still worked for him, so I'm now retired. I was an electronics engineer. However, the history part is still valid. I started this back in 2007 more as a curiosity, because when you look in the textbooks, all you find is the statement that gravity is basically 32 feet per second squared. However, I thought there was more to it. So in engineering, you start with a ballpark number and work the problem from there. Being of electronics type, I was trained to think in waves, harmonics, and frequencies. And like you already said, the wow moment came when all the harmonic wave shapes lined up perfectly with the measured data. The email down there is no longer valid because I'm not employed at Boeing. That's mike.gamble.retired@gmail. As you already pointed out, this study is on the small g of Earth, not the big G of the universal gravity constant. However, my thought behind this was, if you're trying to get off this planet, there's a better way to do it than to fight gravity the way a rocket does. And I think this will shed a little light on it to a lot of people. So we'll just keep proceeding here. This one is the steps I took in understanding gravity. I outlined the tasks, and then I had to split the study into two parts, as the total package would be way too much for a single presentation. It's about an hour now. So the part one deals with the documentation, the math models for a functioning equation for gravity, the research documentation, existing known data, and systems approach for the analysis, because it's more inclusive than just the surface acceleration, which we call gravity. For mathematical analysis, I use MATLAB, and the goal was to generate a mathematical model that accounted for the total systems operation. Now, part two deals with the generation of that equation from electromagnetic, so that is the connection between gravity and the electromagnetic field. And the objective was so you don't have to ride a powder keg to get off the planet. If you just reverse the gravity field, you just float off. Okay, documentation. All this research is from public domain. There's no Boeing proprietary information used in here. Most of the space data came from the NASA website. The Earth structure, core data is from various geological websites. So starting off from physics, what we know, this is your standard textbook classical definition that gravity is a radial acceleration with an average value of 32 feet per second and decreases with distance. It was first discovered by Newton, something about getting hit in the head with an apple. As far as my analysis, I use the equator distance as the x-axis. The polar direction is the y-axis. The radius of Earth at 3,963 miles, and surface value, which is RE equals 1, is a minus 32 feet per second squared. So moving out a little further from the Earth's surface, you come to the Van Allen radiation belts. These are actually two concentric donut-shaped rings that have a crescent half-moon cross-section when viewed from the side. They're thickest around the equator and taper off to 0 at the poles. The inner belt starts about 500 miles above the equator and is 2,600 miles wide. And the outer belt starts at about 5,300 miles and is 6,200 miles wide. Moving out further from the radiation belts is a place known as Geosync Satellites. Geosync for short. This is a place 22,000 miles above the equator where all the communication satellites are parked. It has the unique feature that the satellites at this distance have an orbital speed which exactly matches the Earth's rotation, so they appear to remain stationary with respect to any point on the Earth's surface, even though they're moving at thousands of miles an hour. Little history on there. When I ran my lab, we used to calibrate the inertial flight controllers for the IUS on the space shuttle for every launch. And their job was to, they would load the satellite in the cargo bay, and when they got into low Earth orbit, they would open the doors and unload this. It was called the inertial upper stage, and that would fire out to geosync orbit. And we did all the calibration on the flight controllers. Okay, moving out even further from geosync, you hit the Earth's magnetic shell or a magnetosphere. It's 52,000 miles above the equator. The shell would be a perfect sphere if it was not for the fact that the Earth was traveling at high speed through some type of fluid media. Like a boat going through water, the Earth has a bow wave and leaves a long wake behind it. However, a boat has a rigid bow structure and the Earth does not. Therefore, the front edge of the Earth's magnetosphere is compressed from the impact of this media, somewhere between about 3 and 4 Earth radiuses. And the next piece down there shows the rough speed here. The Earth is traveling around the sun at about 67,000 miles an hour. And a sphere is a very poor aerodynamic shape, though aero is the wrong word. The front of the magnetosphere is compressed, and we leave a wake of about 100 RE behind it because of the poor aerodynamics. Now we'll start number crunching a little bit. It contains a couple of short tutorials on wave shape generation and then on Tesla's work, which is what it's based on. The first tutorial is on relevant mathematical equations and wave shape generation. So we'll start with the relevant equations here. These are the ones that apply to the math modeling. Starting off with F equals ma, which is a standard one from the physics book, that force is equal to mass times acceleration. The equation applies to the analysis in two ways. First, it shows that in the presence of mass, force is proportional or equivalent to acceleration, mass being the constant of proportionality. And second, if mass is placed in a force field, it will try to accelerate unless it cannot move, in which case you have a block force. Moving on to calculus, acceleration, velocity, and position. Your basic calculus shows the correlation between position, velocity, and acceleration. First, velocity is the first derivative of position, and acceleration is the second derivative. This one is a little bit more general. This is the left-hand motor rule out of the physics book, which states that to turn the armature is the force to turn the armature of a motor is related to the flow of the electric current in the field of the magnetics. And then all fields in motion are at 90 degrees to each other. Currently in its present shape there, it's only empirical because you have to put the correct constants in there to make an exact equation. Moving on to wave basics. This tutorial is on basic definitions of waves. It's just background material for understanding wave motion. To start with, show one cycle of a wave up there, and the nodes are the zero crossing points. And the antinodes, if you will, are the maximum and minimums. And the unit wavelength is called lambda, which uses the Greek letter. This one defines wave amplitude. There's three ways of measuring. The first one is the maximum or peak value, which is at 100%. Second one is root mean squared, or RMS, which is defined at 70.7%. And the third is the DC average, which is defined as 63.7%. So using these standard values for conversion of the 32.174 feet per second squared to its peak value comes out to be a minus 0.01 miles per second squared, which is the number I use in the analysis because I have everything converted to miles. And then this one is on standing waves. It shows how standing waves are generated, that you have to have two waves traveling in opposite directions. So when you have a transmitted or incident wave, and it's either partially or totally reflected back, and when those two waves combine, because they're going in opposite directions, there's a resultant is a standing wave. And the problems with it is the phase angles and that. So in the real world, you have to account for the distortion. And it also has the amplitude of the resultant or standing wave is twice that of either of the traveling waves. And the last one here is on polarized waves or rectified. If the reflected wave is half the amplitude of the transmitted wave and double the frequency, then the resultant standing wave is what's called polarized. The wave shape's not symmetrical, as you can see. it's pushed off to one side, and it's usually caused by phase shifting between the two traveling waves. However, it can be beneficial if you're looking for DC rectification. Now we'll get into the wave shape generation, which is the main section, provides the details for the different shape structures and the harmonic placement needed to make them. So we'll start with the radiation belts, or the donut-shaped ring. To generate a wave shape of that type, you need a dipole feed point, which is 2 feed points on the opposite axis. So you get a maximum on the x-axis and 0 on the y-axis. So a dipole is a half wavelength at the frequency you're talking about. And so when you transmit out, there is a node. Whoa, what was that?
Oh, I'm sorry about that. We had someone unmuted themselves on accident. Go ahead, Mike. My apologies.
Anyway, there's a 0 point in the middle, and then there is positive acceleration on the inner side and negative acceleration on the outer side, which pushes that shape. So the wave shape coming through on the x-axis, it starts going positive, and then it goes through 0, and then negative, and then back to 0. The further up you go, the less that S-shaped birdie is. So that wave shape of that pattern and a half-wave dipole will generate your donut-shaped patterns. Now, the wavelength, which is the inverse of the frequency, determines the pattern size. So now we'll go to a sphere, which is very similar. It's a little bit simpler. This one only needs a single feed point located at the center. And then the principle is the same. So you're getting the same amplitude on the x-axis and the y-axis. The inner circle has positive acceleration on it, and the outer edge has negative acceleration, and in between there's a node or a 0 point. So you get this S-shaped birdie, is what I call it, in the acceleration wave. Now this next chart, this is one of the most important ones in there. When you line up everything that you see going out from the center of the planet to geosync orbit, that turns out to be one wavelength. And if you go from geosync out to the edge of the magnetosphere, that's 2 wavelengths. So from the center of the Earth to the edge of the magnetosphere is 2 wavelengths. Now there's another interesting one, that the outside of the planet, which includes everything, is also 1 wavelength circular. Now, I do apologize for drawing these waves as just straight lines, because they're actually vibrating up and down. However, if you put too much stuff or information on a chart, it gets a little bit confusing. So I just use them as straight lines, but you need to realize that these are actually standing waves. Now we'll take a detailed look at the circular wave that covers the Earth. It covers everything from, okay, this here is the crust, then you got the atmosphere, and then you got the ionosphere, and it provides the outer edge of the ionosphere. So you come over here, the surface of the Earth is 3,963 miles. Air, which is the blue, goes out another 50 miles, which is 4,013 miles. And then the top of the ionosphere is about 230 miles out, so you're 4,194 miles. And like I said, it's completely enclosed by the fundamental frequency. Now we'll take a rough calculation on estimating that frequency. So if you use the wavelength, which is frequency over C in lambda, first one going using the Geosync measurement gives you 7.12 hertz. If you use the Earth radius one, it comes out to be 7.07. So if you average those two, the estimated frequencies is 7.1 hertz for the fundamental. Second harmonic is 14.2. Third harmonic is 21.3. And the fourth harmonic is 28.4. Now we'll go back to the picture there, which was on figure 5 of the Van Allen radiation belts. Only now we're going to move them over to wave harmonics instead of distances. So measured from the center of the Earth to the center of the field is 1/4 wavelength for the inner belt. The outer belt is 1/2 wavelength. So it's 1/4 lambda and 1/2 lambda. Now, Tesla had these numbers. He was well aware of the radiation belts at 1/4 lambda and 1/2 lambda. However, he had no data on geosync orbit or the magnetosphere. The next step is what the planet core would look like, depending on what the acceleration at radius 0 would be. If it's negative, it gets squeezed together and you have a solid. If it goes to 0, you're going to have a small hollow and a thick crust. And if the acceleration goes positive, the crust will get thinner and the hollow will get bigger. So we have to work with 3 types until we determine what it is. So now, next step is we take all these little previous charts and we put the whole picture together. And what we come up with is, okay, we have one wave that's positive, we have one wave that's 0, and one wave that's negative at the center. And then they all have to pass through the surface acceleration point of a minus 0.1 miles per second squared at the surface. And then they go flat until you get out to geosync. Oops, I just pushed the wrong button. Let's try that again, which sets out here at 6.6 RE or 26,154 miles, which is from the center out to that point is 1 wavelength. And then if you went out 2 wavelengths, you'd be way out there, but I don't have the scale showing. Okay, then you take all 3 of those waves and you do what's called an FFT, fast Fourier transform, to look at the subharmonics. And what you see is, okay, the dotted one down here is the thin crust one, and it's way out of shape because you need a descending value with frequency. So the only 2 that work are the thick core and the solid core, which are these 2. And you see you get 3 waves in descending order, and they're all listed there. Okay, the next one is we do the same thing over on the x-axis, where we take positive acceleration, a 0 acceleration, and a negative, and they go through the same surface marker. Only now you have another birdie here for the inner belt at a 1/4 lambda, and one in here for the outer belt at a 1/2 lambda, and then the same one out here for geosync at 1 lambda. And running a Fourier transform on them, you get very similar wave shapes, only you now have 4 harmonics instead of just 3. And again, your thin crust does not work there. It's one of those 2 is the one that's going to work. Okay, now we have to stop and talk about the error from the Fourier transform. It has some problems, but like all mathematical things, when you use it, you lose the phase data. So when you try to reconstruct the signal, you have to supply the phase data. And there's also what's called a quantization arrow, which is the width of the frequency bin. I set this just under a half a hertz, so it does give some, reduces the error. And then the amplitudes are all relative also. So if you want absolute or the real amplitudes, you have to supply those back yourself. So there's two problems. One is phase and the other is the real amplitude. However, it does a very good job of showing the subharmonic components, which is what I use it for. Okay, now we start putting the picture together. On the y-axis is generated by 3 harmonics, and on the x-axis it's generated by 4 harmonics, and you have the 3 core types. So now getting down to the frequencies, the estimated frequencies that we're going to run are here, and these are the frequencies from the data that we just did with the Fourier transforms. And as you can see, they're all very, very close. The higher the frequencies, the closer they seem to get, and then you have your error of half a hertz. And as the proposed numbers and the estimated numbers all seem very close, there's a very high confidence that the original assumptions are true. So now we start generating our equation. We're going to have 4 harmonics, and then we have 4 phases. 0 degrees is the sine function, 90 is the cosine function, 180 is a minus sine function, and 270 is a minus cosine. So we start with acceleration is equal to some constant a, and it's either sine, cosine, sine, or minus cosine for the fundamental, and then the same for the higher harmonic. So what you wind up with is a 4x4 matrix, which gives you 64 possibilities. And when you run all those numbers, there's 5 combinations that produce a hollow core, and there's 6 combinations that produce the thin crust, and 7 that produce the solid, and the other 46 combinations just produce random garbage. So now what we have to do is take our equation that we're generating and compare it back to the data plots for both the X and Y axis for the different core types and see how things start lining up. So this one is for the thin crust, where you have positive acceleration, goes to 0, and then you get the geosync birdie. Okay, now our equation is a minus 16 sine 707 hertz, minus 16 sine 14.3 hertz, plus 12 cosine 21.2 hertz. And that's your dotted line here. So the acceleration is higher, comes down, it goes through the surface marker, wobbles a little bit, and it doesn't do much out here at the geosync point. So it's probably not right. So then we pick the next one, which is hollow core, which is the 0 acceleration point. And we come down, negative acceleration, and it goes through the surface marker, and it just lays right down flat on the picture, 1 to 1. It's minus 20 sine 707, minus 20 sine 14.3, minus 8 sine 20.20, or 21.20, excuse me. So there's a very good possibility that that is the right one. And we'll check the other one just to make sure. The solid one, which is negative acceleration, comes in at minus 20 cosine 707 hertz, minus 20 sine 14.3, minus 20 sine 21.2. And as you see, it picks up the surface point, but it doesn't line up all that well either. So going with the x-axis data. I'll cheat a little bit, and I'm only going to run that one number, which is the hollow core one that with the thick crust. So we start with 0 acceleration, goes way negative, comes through the surface marker. It has a birdie at 1/4 lambda and another birdie at the half lambda, and it has a pretty good one line up at the full lambda. The equation is -20 sine 707 hertz minus 40 sine 14.3 minus 26 sine 2120 and minus 26 sine 2827 hertz. So those two, the hollow core, thick core data, appears to line up fairly well with both the X and Y axis. So now we'll do a little bit of analysis on there and looking at it. Right now, I'm using a single feed point at the origin. And so the hollow core thick crust tracks best. And the inner belt location is just a little bit off. Frequencies and amplitudes line up in spite of the quantization error. However, when I change to the feed point to a dipole, there is a possibility that there's going to be some changes in the shape. So now we start converting over and looking at the data. At the 707, which is your fundamental, the gain factor on the x-axis, or the amplitude, however you want to look at it, is 20. On the y-axis, it's 20. When you go to the second harmonic, 14.13, the gain goes to 40 on the x-axis and 20 on the y-axis. So it's twice as big, 2x on the second harmonic. The third harmonic goes down 2120. It's 26 on the x-axis and only 8 on the y-axis. So there's a gain of 3.25 on the x. And then, of course, the fourth harmonic is the one you want to zero out. You got 28.27, which you want to gain on the x-axis of 26, and you want it to go to 0 on the y-axis. So you now go to a feed point, which is a dipole, which is half lambda on the fourth harmonic, which will zero out the fourth harmonic on the y-axis. And then you bring that down, converting from the fourth harmonic half lambda down to the fundamental, which is by 4 times. So at the fundamental, it's lambda divided by 8 is the spacing of the dipole that you have to put in there. So when you put it in there and run it, this is what you get. The acceleration is equal to -10 sine 707 hertz, minus 15 sine 14.3 hertz, minus 11.55 sine 2120. Uh-oh, pushed the wrong button again. And then the fourth harmonic is 10.65 sine at 28.27. And if you look at it, the thing just lines up perfectly. And it goes up here, you have your inner belt, your outer belt, your geosync, and then it comes out here to the outer magnetosphere, which is 2 lambda, 1 lambda, and it just absolutely lines up perfectly. That was the wow moment in my research. I didn't believe that it could line up the math model against the real world that perfectly on the first cut. And one thing you notice here is going to the dipole feed, the acceleration at the 0 point went totally negative, so it's a solid core. However, if you take a close look at the surface marker here, you'll see it's just a little shy of the 32.5 feet per second squared. Now the next one is we run the same equation, 10.05, 15, 1155, and 1065 on the y-axis. Now you can see the dipole here because it's positioned on the y-axis. You get the same, this is what's known as the gravity well, and then it comes up to the zero. You get your geosync and your outer marker. Those line up perfectly. Now, looking at the surface point here, you see it's just a little bit greater than the 32 feet per second here. So the next chart, the planet has to be a little out of round. It's not a perfect sphere because the poles are squished just a little bit because the dipole puts the amplitudes a little greater on the y-axis than on the x-axis, so they get squished a little more. Now going back, this is another one of the important charts in this presentation where you take all the waves and superimpose them on the planet. So the first one is the fundamental that wraps all the way around. But if you look at where the second harmonic, third harmonic, and fourth harmonic, they're all in the outer core. So you get all the details here. That first you got the crust material, which is solid and brittle, and the brittle is what earthquakes fracture to make mountains and valleys. It also conducts electricity, and all the world's power grids are grounded to it. Second, moving down to the mantle. The mantle is more plastic or pliable, viscous, if you want the technical term. Its composition is mainly silicates with a little bit of iron. It's also the material that volcanoes spew out as lava or igneous liquid in igneous rock. And the mantle's under high pressure and high temperature. Third, the core material is composed mainly of iron and nickel, the outer region being in the liquid state. And the inner region is fairly solid due to the high acceleration point. That spike squeezes it pretty bad. Now, this is the interesting point. As the core material is under so much heat and pressure, the Curie point cannot maintain a magnetic field on its own. Now, there's a lot of iron down there, but because of the heat and pressure, it will not hold a magnetic field. Now, any Boy Scout knows with a compass that the Earth has a magnetic field. Well, that implies that that field has to come from the electromagnetic field that generates the gravitational field, because the center is above the Curie point, so it cannot maintain its own field. And you see that all the higher harmonics are all in the liquid media. And what happens, because these are standing waves, you get some mixing and stirring, which causes the heat and the pressure. And it also works like a motor armature as this core is spinning, only it spins much faster, which is like revolutions per hour versus revolutions per day for the Earth itself. Now, the second function that happens or due to the mantle is you get an automatic spin balancer. You have a mass here and a mass out here, and you have essentially a spring or a viscous fluid between them, and that dampens out the vibrations. If the crust moves out of alignment, then pressure builds up and in the mantle, and that restates it. Now, if the pressure gets too high, there's a safety valve called a volcano, which will pop and vent. And then for stability, when the heat generated equals the heat loss and the spin power equals the drag, then the system becomes stable. Now we're going to go and take all the 2D information that we've been working with and plotted in 3D, so you get a very good picture of what's going on. This is the side view. Okay, here's your surface acceleration right here. This is the big gravity well that everybody's using rockets to get off with. There's your feed points. And then you come out here, you have your quarter wave radiation belt, your half wave radiation belt, your geosync orbit, and your magnetosphere. But you see one wavelength out, it is still going through space. So it doesn't end at the magnetosphere. You still have increasing waves. However, the amplitude goes down. Now this one I twisted over and put a contour plot on the bottom, which shows it a little bit better. You can see the quarter wave, the half wave, full wave, and two wave, or 2x there. So then there's the third cycle, fourth cycle, and each one, of course, the amplitude diminishes. If you take those 4 waves with that equation and do the transform on them, you get 2 waves, the 7 and the 14 fairly high, and then you get a decrease for the 21 and the 28 on a decreasing scale. Now we'll talk a little bit about Tesla and his Colorado experiments. They're relevant to this study because he measured the electromagnetic spectrum of the Earth along with a lot of other things that he did. To start with, what he measured was 7.8 hertz at 0.12 milliwatts per hertz, 14.1 hertz at 0.1 milliwatts per hertz, and 20.0 at 0.06, and 25 at 0.05. Now, if you look at those numbers, they're very close to the gravity numbers, almost too close not to be connected. So when you do an FFT on them, you get this nice wave shape here. And if you look back to what was generated off the gravity equation, you have your 7 and your 14 up high and your 21 and 28 down low. Like I just said, the correlation is too close not to be connected. Now, moving on, this is the Schumann resonance numbers. He added a fifth harmonic, a 32.4. Tesla's numbers disappeared for many years, and about 1950, a guy by the name of Schumann started doing some research and essentially rediscovered Tesla's numbers. Feel bad about Tesla because he doesn't get much credit for any of his work, electric motors, power grid, etc. However, I am of the opinion that he knew a lot more about gravity than what he was letting on, because I think he did the research. Okay, now we'll wrap this up and summarize the major points. And what we get is gravity compiles all the data and information from the research, and looking into the subject, the gravitational system of Earth is composed of an accelerating force field comprised of low frequency standing waves, which do far more than just generate the 32 feet per second surface acceleration, which we call gravity. They extend out some 60,000 miles, which is 2 wavelengths into space to generate the magnetosphere, the geosync orbit, and both the inner and outer radiation belts. This wave shape is composed of a fundamental of 7.07, 14.1 for the second harmonic, 21.21 for the third, and 28.28 for the fourth harmonic. Looking the other way towards the center of the Earth, the fundamental determines the outer edge of the ionosphere, or the edge of the Earth system. The three higher harmonics reside in the core, which causes the heat, the pressure, and the rotation of the planet. And these waves are all sourced from a dipole feed point located on the y-axis, separated 1/8 lambda on fundamental frequency. And it also changed going from a single feed point to the differential or dipole feed. The core type changed from hollow to solid. And second, there's a flattening of the pole regions, which makes the sphere a little bit egg-shaped. And the third one there, it generates the crescent-shaped inner and outer radiation belts. The first three harmonics primarily determine the planet structure, the geosync orbit, and the magnetosphere. The fourth harmonic seems to contribute more to the two radiation belts. And follow-up in doing the data reduction and number crunching, I came across two facts. They're not directly related to gravity study, but I think they should be documented as well. First, it appears that frequency determines the size or the scale factor of the structure. If this comes out to be true, then atoms would have a similar structure, only a very high frequency. That would be like gigahertz or terahertz, instead of down there at 7 hertz. And second, the waves of acceleration seem to be of electromagnetic origin, because they track the two too close not to be connected. That's Tesla's data and also the Schumann resonances. And that's the part that I work on for the analysis of the electromagnetic spectrum in the second part of the gravity pitch. That one's not as easy to understand because it's field theory. Anyway, that's all for this one. Now, Tim wanted me to go and pitch a quick one on gyroscopes, which is what I'm going to try and do next here.
Yeah, Mike, I would love that. Well, we have you, and I'm happy to split that up into both. Well, before you do that, then let's do this. Let me put it on gallery view real quick. Here, let me stop your screen share. And again, we need to have a real applause here because that was pretty in-depth. So everybody, let's, I'm not going to unmute you, but let's have applause for presentation number 1.